All the participants on behalf of Akshay webinar series, welcome. Today's webinar is future of intersection with quantum computing. Here today, personality actually from quantum technologies and along with the quantum. Before welcoming today's research person, I wanted to introduce this brief biodata to the participants. We working with Wiser, that is Washington. I'm happy that from tomorrow and from 8th onwards, the AP government, in collaboration with Akshay, is going to conduct student on quantum technologies and algorithms. So here is the man who is behind this Wiser program for the students. He is Vardhan Sagar. He is a quantum computing researcher with a background in atomic physics and experimental material science, and he has over 7 years of experience in the quantum technology domain. As the quantum solutions head at the Washington Institute for STEM, Science and Technology, Entrepreneurship and Research, he leads initiatives that guide Fortune 500 companies in leveraging quantum computing to gain a competitive edge across sectors such as energy. Wow. He is being recognized as a young pioneer under 30 in quantum technology in 2024 and nominated for the All-Star panel at Quantum Technology 2023. Vardhan is a thought leader in quantum innovation. In 2021, he received the Global Community Award by IBM for his contributions to improving quantum circuit efficiency and exploring NISQ era applications for real-world business use cases. A prolific contributor to the scientific community, Vardhan has authored several research papers and business reports, and won over a dozen moonshot industry charts and hackathons. Beyond his technical expertise, Vardhan is actively engaged in business development and educational outreach, supporting startups and academic institutions throughout the Asia Pacific region. He is a member of the GESDA Open Quantum Institute and provides strategic advisory for various international quantum missions. Here it is very brief about his achievement contribution to the quantum technology as well as AI. But today's research person stand tall. Vardhan Sagar is the future of AI and its intersection with quantum. With the quantum strategy solutions head as an enterprise quantum transformation. Vardhanji, actually, as you know that, as we have already MOU with the government of Andhra Pradesh and main stakeholder in training the students, I appreciate your initiative and your support to Andhra Pradesh and particularly the Amaravati Quantum Valley. And apart from this Amaravati Quantum Valley, we are also having so many industries coming up in Visakhapatnam, that is artificial, etc. But from Google, Microsoft, Adani, Reliance, etc. In this background, there is much scope for all our AP as well as faculty to work on this both Quantum Valley as well as the data centers and AI. So in this connection, we link both the quantum technologies and AI also, so that it can be for all faculty. And simultaneously, we have shared YouTube live link to all our students, where the students can simultaneously connect to you and your talks. So with this brief introduction, I now welcome, and it's our honor to welcome you for this. Before talking to the students, it's an opportunity. So very intentionally engaged you for this webinar series, and I request all our faculty members tomorrow also during this launch and also please connect this Wiser training program for 50,000 students. Maybe I think so far, as far as the quantum algorithms, at a time 50,000 students training is is a great news for us. And thank you very much for your contribution and support for AP as well as AP State Council of Higher Education. On behalf of our chairman, Professor K. Madhumurthy Garu, I welcome you because he is the vision. Simultaneously faculty as well as students on quantum technologies and quantum algorithms, and also we are also faculty as well as students. With these few words, I thank Akshay and Chairman. Now the floor is open for you, sir.
Okay, wonderful. First of all, thanks a lot. Thank you. Thank you so much for inviting me over here. I'm humbly honored. So first of all, great support from Akshay, from Anilji, and from Professor Madhu, who has been the leadership in there. Akshay has been really helpful for us in expanding into India. So I'm really, really grateful that I'm here today for this webinar, but also in a couple of days for our flagship program that's going to be launched in India, first in Andhra Pradesh. So today's session, I'll quickly start sharing my screen as well. It's going to be about the intersection of quantum and AI. And we'll be talking about a lot of different things. I'm not here to give a one-sided lecture. So we'll try to make this meeting as interactive as possible. I hope everyone has access to the chat. So we'll continue chatting on the chat, right? I have it open on my end as well. So we will try to make it as interactive as possible. I'll have questions, you will have questions, and together we'll make sure that at least for the next 60 minutes or so, it's productive on both ends. Right? So I'll try sharing my screen. But while I do that, let's start off with some quick introductions, right? So I'll get on to my introduction very quickly, but before that, I'd love to hear who all of you are joining in from, right? So whether you are professors, whether you are researchers, whether you are research scholars, students, undergrad, masters, please introduce yourself in the chat on a very where you're coming in from and what university you are representing, right? So quickly, I would love everyone to just put it in the chat of what organizations you're representing and what's your quick introduction. And meanwhile, I'll start sharing my screen as well. Okay, here we go. So I already see 2 messages. Thank you, Chandra. Good morning as well. Great to see you over there. Velenki Chandra, thank you. Thank you for joining in. I have Dr. M.L. Kiran, Professor and Dean of Srita Produttar, Andhra Pradesh. Welcome. Thank you for joining in. Wonderful to have you here. Dr. Nona from Raman Lecturer at Government Degree College, Darcy. Thank you for joining in, Dr. Nona. Dr. Nana Penny, Dr. Radhika, welcome, welcome. Dr. Mandam, Dr. Sudhana. Okay, I love this. I have a lot of professors joining in. Any research scholars or anyone who's coming in from a different perspective, I would love to hear from them as well. We have Dr. Balaji, assistant professor. Okay, wonderful. Yeah, let's keep the introductions going on in the chat. This is really nice to hear. Welcome everyone. From where I'm sitting, I'm currently in Delhi, in India, and if I am at a small cafe kind of place right near to IIT Delhi. If you have been there, if I look to my right and if I try and squint my eyes, I can actually see Qutub Minar from here. The smoke is terrible. The pollution is at an all-time high, so I can't really see that. But you get the idea, right? Otherwise, the weather is chilly. I think the weather is almost at 10 degrees Celsius, which is really cold. I would have really loved to just rotate my laptop and get you outside and actually try and see the beautiful landscape from here. It's really beautiful, but it's too chilly for me to go outside. Anyhow, it's really nice weather, and I'm sun shining. It's good. I hope everything is really pleasant in AP as well. And with that, let's get started today. So today my talk is going to be about the future of AI. I must say I'm not an expert in AI, but I am an expert in quantum computing. So that's where the intersection is, where we are seeing. I work out of Visor. Visor is the Washington Institute of STEM Entrepreneurship and Research. So I'll talk a little bit about that as well. To give a quick introduction about myself, although Anilji did a pretty good job, so I'll keep it very brief over here. I started working in quantum many years back in 2018. At that point, everyone was claiming here and there what is quantum, what the different quantum advantages are. And gradually, it's been a slow journey. We realized that even though quantum computers are there, even though we are working today with some of the best quantum algorithms, quantum advantage is still a little bit further away, right? So we want to make sure that we all work together towards that. In 2020, I first got introduced to IBM, and since then, I formally started working in quantum. I went to IIT Delhi, worked there as a graduate TA, then went to University of Bristol, tried to do a PhD. It did not work out for me. Moved across the pond to US, worked at MIT, and currently I lead the quantum solutions team at Pfizer. Along with that, I also have some roles at as a Qiskit advocate at IBM and as an Open Quantum Institute member at OQI. So OQI is incubated at CERN in Geneva right now. They're working over there as well. So the overall goal is still the same, right? We want to accelerate quantum. We want to build quantum ecosystem, not just in the US, but also in India, all across the world. And we want to make sure that we're all working together towards the development of this new upcoming technology, which is called as quantum computing. So we are all working towards that. And just like Anil just mentioned before my talk today, right? Like we are working very closely with the government of Andhra Pradesh, and we are very, very happy that they are putting in so much effort, and I love their leadership coming into all of this. We really see AP coming the national capital, not just the national capital, the capital region for quantum computing, AI, and all of digital technologies for the entire APAC region. So we are really, really excited over here. And with that, let's continue with the discussion today. So I'll talk about why is there a need for quantum? So that's the first logical question, right? We have had the IT boom, then we had recently the AI boom. Where is all of a sudden quantum coming in? So we'll talk a little bit about that. We'll talk about what quantum computing is all about, what are the different applications about it, and then we'll understand that even though quantum is very good, we all want to do quantum. It's not below its share of difficulties, right? So we still have a lot of bottlenecks in quantum computing, and that is where we see AI contributing the most. So we will I'll share today a few ideas on where AI can be helpful for quantum. And that would be an open question to all of you, right? Because all of you are much, much more talented than I am. You're much more talented in research and have much more experience on how to integrate and develop the best AI solutions in the world. So that would be my ask for all of you, right? So I'll give you the problems. And in the next couple of months, I sincerely want all of you to at least start thinking about that. Try to involve all of your student community, all of your research community into thinking how can AI be useful for developing and accelerating quantum in the next few years. We already have a few industry use cases as well, so I'll shed a little bit of light on what we are developing over there. And then the future, as we all call it, right? The future would be a mixture of quantum and AI, so we'll talk a little bit about that as well. So yeah, with that, let's get started. I still see a lot of things on the message chat. That's lovely. Please keep the messages coming. I see a lot of professors joining in. Thank you sincerely so much for taking out time early this morning on a Saturday. So I'm really grateful that all of you could take out time from your busy schedule. So wonderful, wonderful. Let's get started. So the first thing is for all of us to understand is that, right, that why even quantum? We were happy with IT. We were happy and really, really happy with the entire AI boom. So what is actually the reason behind coming to a stage where we very importantly need quantum computing to enter? And one of the reasons which we like to share is that Moore's law is unfortunately decelerating, right? So for decades, Moore's law has provided a very reliable roadmap. I know Moore's law is very, I would say, trivial in nature. It's elementary, but at the same time, it's been a reliable benchmark for the industry because it has provided kind of a roadmap for performance growth. And unfortunately, since 2013, that trajectory has very fundamentally changed. The performance improvement is no longer that significant. The supercomputers that we have been building are not accelerating at that kind of a legacy, at that kind of a historic rate. And you can see that very evidently on the graph on the screen on the right-hand side as well, right? So for many, many years, the acceleration and the performance was shooting right up. But after 2013, that growth has been very slow. And the yellow curve shows the rate of decreasing in the performance, right? It's not particularly decrease in the performance itself. It's more so decrease in the performance advantage that we have been getting over the many years. Right, and that's one of the reasons why we need newer, better compute technologies, because AI is dependent on classical technology, and if the classical compute itself is no longer moving at a very fast pace, maybe we need something else, right? So that is one of the very fundamental reasons why we had to just think beyond the box and try to seek new computational paradigms for digital technologies. So yeah, that is one of the major reasons why we are looking at quantum technologies. But that's not all, right? One other reason is AI itself. It's kind of hitting a roadblock with energy demands. So AI is today, but scaling today's AI with supercomputers and HPCs and data centers, it's terrible. It's creating a very unsustainable power crisis. So if you see on the graph on the right-hand side over here, right, you'll realize that the rise of these GPU-accelerated systems has provided some kind of a temporary performance boost, that we are all happy that everything is moving very quickly. The data processing speeds are at an all-time high. I must say that we are very proud of that. But at the same time, the power consumption of some of the world's most efficient systems is just exploding. And that explosion is very significantly visible on the graph on the right side, right? If you see the amount of power that has been getting consumed right from the 2020 timeline, it's huge. And this consumption of excessive power, oh my God, it's posing a significant challenge for data center providers, for society as a whole, and we all just need to understand how hyperscaling this can be. Yeah, we need to find a valid solution for this, right? Not everyone, or just as a humanity and the world in itself, right? We cannot afford that kind of power consumption for AI and for data centers and everything. So nuclear power plants is one alternative that we all are already thinking about. But even then, some startups are thinking about sending data centers to space. But yeah, all these are possibilities. Let's keep working on that. One other possibility, as we see it, is just have a new paradigm for quantum computing, right? So we've had a history where the computing was defined by transformative shifts. The invention of the GPU demonstrated and kind of democratized how we accelerate scientific computing with CUDA. And then this was fueled by another big revolution, as we call it, the AI Big Bang, which fueled deep learning revolution. And now, as we all see it, right, the Moore's law is decelerating. The CPUs are almost at a stage where they're becoming extinct. And the next big thing, as we call it, is the quantum era. We are just at the beginning of that. This is kind of a flagship moment for everyone in this ecosystem. Try to extrapolate yourself and imagine yourself at a stage where computers were 100 years back, right? When they were just getting started, when we had computers the size of a room, right? So we are at exactly that stage in the quantum computing era. The progress is very fast, but still there's a lot of fundamental research required. And given the state of AI today we truly believe that AI technologies can help quantum computing, and that is what is going to be my core topic of discussion today, right? So yeah, as I mentioned, right, the future of the entire computing era would be quantum. We have had classical, we have had AI. The next big thing is quantum, right? And saying that, I don't want to sound very pragmatic over here. Sorry, I don't want to sound very agnostic over here. I want to be very pragmatic. And having said that, I also want to say that it would not be purely quantum. The future, as we see it, would be kind of a mix between quantum and HPC and AI and everything combined together. And when I say quantum, it has huge applications, right? So one very common application, as you might find in this quantum computing space, is for finance, or it could be for different kind of applications in search, in cryptography, in data science. So any industry you can think of, people are already applying quantum computing to that. And the reason being, they're thinking 10 years ahead, right? Because if you're a company working at that scale where you have billions of dollars as a market cap every month, every year, you need to think at least 5 to 10 years in advance. Because if you are not thinking that way, you're already lagging behind your competitors, right? So these companies are already thinking, how can they get an edge on the competition? How can they start planning for compute resources that are already getting extinct? AI resources are already in huge, huge demand. So they cannot run after that every time. They need powerful machines. They need to start thinking out of the box. And one common thing in all of these idea and thought processes that everyone is interested in quantum. Everyone wants to see where can quantum help their businesses, where can quantum be intersected with their research. And today, as I see it, there are a lot of applications. Everyone is focusing on different kind of these domains. And if I can give you one homework for everyone over here, right? I know all of you are professors, or at least most of you are, but maybe as a working exercise after this lecture is, right? Try to see what are some of the most pressing problems in your niche domain of research, right? And then see, can quantum be somehow intersecting with that, right? Because you're the best people to help us understand that. You're the ones who are going to tell us that, hey, this is a problem that I've been struggling on because we don't have compute resources that are good enough. So maybe, just maybe, there is the chance that quantum computing might be helpful over here, right? So you're the best people, you are the domain experts to tell us where quantum can fit in. And then obviously quantum computing specialists can come in and help you out with understanding what exactly is the intersection, what's the synergy, and how we can collaborate together and work this problem out, right? How can you find the solutions to these problems? So when I talk about all these solutions, right, try thinking about another aspect of it, that it's already been applied. It's no longer a new shiny thing in the market that everyone is running after. It's up to a tier level where industries are already starting to adopt. And one very, very good example that I often share with everyone is the recent report that was released by NERSC. Uh, so NERSC, if you're aware, is one of the largest supercomputers in the US at LBNL. And that's the Lawrence Berkeley Livermore National Lab. And over there, if you see the kind of workloads that have been running over the past year or so, you will realize that majority of them are quantum in nature, right? The world's biggest supercomputer, if you just see the pie chart on the right-hand side of the screen, you'll realize that maximum problems that are actually being run on these supercomputers are quantum in nature. So we bloody hell need quantum to solve them, right? It's so obvious. We can see that on the kind of demand that we're already seeing on the supercomputers, and the way we like to divide this is that there are maybe three sets of problems being run today on supercomputers, right? So one is a, a problem that is quantum inherently. These could be the problems that are right now showed with a green quantum sign on the pie chart, the quantum chemistry problems, DFT, lattice QCD problems, and stuff like that. They have quantum properties embedded in them. So it is just very obvious to see if quantum computing can be helpful over there, right? It's a kind of intuition already coming to us. The second set of problems that we see over here that have been demarcated with the blue quantum sign on the pie chart, something like a fusion problem, right? Or n-body multi-dynamic problem, something like that. So these kind of problems are not purely quantum inherent, but they still show properties that we as researchers feel that there might be certain quantum algorithms that could help accelerate the research on these, right? So again, a very promising area. But yeah, obviously that's the third set of the problems that we see. These kind of problems are, I would say, classical. They're purely classical, so we don't necessarily need quantum, and that's okay, right? We have a nail, and we don't need to find every particular tool to fit that nail. We just need one good hammer to push it in, right? So we have problems. We are already seeing it as per the demand of the supercomputers, of the world's largest supercomputers in the world. And it's already indicating that quantum will be the future, if it's not already. It's a significant portion of the work that we are already performing at these national level supercomputing centers is quantum mechanical in nature. And this already suggests, as I mentioned, that the quantum algorithms that are required It's already in play. We are already developing these kind of algorithms, and now it's up to you guys, right, to help us understand what all other areas that we can figure out. What are other lines and what are other niche areas in the industry for classical computing where quantum can be helpful. So yeah, that's kind of the motivation where we are coming in from. Everyone is excited about quantum, and we're already seeing a lot of promise for them. So yeah, let me maybe quickly take a pause over here to see if we have any questions, right? And if there are no questions, I would rather ask all of you a question. So if, let's say, tomorrow, or maybe by the end of the day today, all of you have access to the world's best quantum computer, right from your laptops through cloud. What are some of the problems that you would like to challenge? What are some really, really difficult problems that you guys are seeing that could be helpful with quantum computing, right? All crazy ideas are more than welcome. I'm nowhere to judge anything from you guys. So yeah, let's try and see what kind of ideas you all are thinking of in the chat, right? Take a minute, try to write something down, and maybe I can start with something, right? For example, I'm sitting here in Delhi and I hate the pollution. Okay. So maybe quantum computing can help improve the pollution in the national capital of the country. Yeah, so that's a good idea. Another thing I really struggle with is traffic. So I was in AP like a few like just last month, right? A few weeks back. And I was surprised how clean the city was, how easy it was to move from point A to point B. And maybe I was not exposed to the entire large state of AP, and that's okay. But you come to Delhi once, you realize the crazy traffic we have to deal with over here on a daily basis. But yeah, that's maybe another thing, right? Optimizing traffic routes, optimizing logistics. That could be another thing where quantum computing could be useful. So yeah, I'll keep an eye out on the chat throughout this lecture. If there are any questions, please feel free to put them in the chat. If you have any crazy ideas as well, again, uh, please feel more than welcome to put them in the chat. We'll all be very interested to hear what you have to say. Yeah. So with that, my kind of the pretty image that I'm painting over here is that quantum computing is very good, and that's wonderful, right? And that's going to be the future. So the future would be a mix of quantum computing, where we are getting something from the quantum side. We are still having some sort of a classical compute in the place. The path forward is kind of a hybrid solution where each processor is defined for a specific task, and so the fundamental idea is that, right, quantum computers won't replace your mobile phones, for example. They won't replace your laptops, right? They would be specialized tasks, very similar to how GPUs are working today, right? Even though we have GPUs very closely tied up with classical computes, they're not necessarily used for everything, and that's okay. We need them when we want them. So similarly, quantum would also be used for very specific niche problems that require them, but not necessarily for problems that do not require them. That's okay. So that's the kind of future that we foresee for quantum computing. And I have a very wonderful question in the chat right now. What are the drawbacks of quantum computing? And that was the next topic I was just going to share, right? So for now, I've been painting a very pretty picture for all of you. And I did that purposely because I wanted all of you to at least get hyped up that quantum computing is the best thing in the world. Let's all leave our day jobs and put all of our eggs in the same basket, and let's all start exploring quantum computing. Fair. But it's also our responsibility to make sure that the drawbacks, the bottlenecks of quantum computing is also fairly explained. So we are at a stage in the quantum computing where we see a lot of promise. We we see that quantum computing advantage is very near, but still the road to that is not without its own share of problems, right? So however significant breakthroughs we might see in the quantum industry, the qubit qualities, the scale at which this is required, and the overall technology stack that is required to unlock quantum's full potential, it's still a few years ahead, right? So today's quantum processors kind of exist in a very noisy environment, and that is where we call them the NISQ era. That's called the near noisy intermediate scale of quantum computing. And to really achieve the so-called true quantum advantage, you see, the hardware must move into a state where it's a regime of both high qubit counts and at the same time very low error rates. So if you look at the graph on the right hand side, we need to move up and to the left. So more the number of physical qubits, it's better, and less the error we get in these qubits, it's again better. And the problem is not just hardware. Please don't get me wrong over here. It's not just hardware. We're not only blaming the hardware engineers over here. The software engineers are lacking at the same pace. So we need better scaling resources for quantum error correction codes. We need much more resourceful algorithms out there. We need faster decoders, for example. We need better device control. We need better control electronics in general, right? We need more efficiency. And overall, just dramatic improvements are required in this entire quantum computing stack. So, like I mentioned, and thank you for that wonderful question in the chat, right? Quantum computing is the future, but it's not without its own share of problems. So to get to that promising land of quantum future where everything is much more faster, much accurate, and we can solve many big problems, we all need to work together to solve the current problems that we are facing with quantum computing, right? And one way to do that is to get help from AI, because AI is just pretty cool, right? So today we are already deploying AI across the entire quantum stack. And this can be understood by using AI for algorithms, using AI for different kind of optimizations in the circuit compilation itself, or using AI for quantum error correction. It makes sure that the complex tuning and then the operations of these kind of quantum processes are well handled, right? Or for hardware control as well. So we need AI for a lot of different things in quantum itself. And that is why I mentioned today the one thing which you might take away from today's entire discussion is this slide, right? So feel free to take a screenshot or something like that, because that is the open question for all of you. Where can you all bring in the AI expertise that you are best familiar with and help me, help my team, help all of the quantum researchers out there who are struggling with these kind of problems? And I'll take maybe the next 10-15 minutes to discuss in detail about what exactly these problems are and where and we exactly see an AI advantage coming in. But please don't restrict yourself to what I'm saying, right? Try to think beyond this as well. Try to think about these problems in general. What are the different kind of AI tools that you are most confident with? What are the kind of the state-of-the-art research that you are all leading at your universities, at your labs, at your research institutes that can eventually be helpful in the quantum computing domain at some level, right? So we need a lot of help over there. I won't be shy at saying that. We are still struggling a lot with making sure that quantum advantage is near rather than in the later future. It's a lot of promises there, but the path to that is also difficult, right? So that's kind of the bottom line of today's discussion. Yeah, so before I begin sharing a deep dive into what these kind of domains are where quantum and AI intersect and where AI can be really helpful to all of us and what's the kind of research that we are doing today, I just wanted to give a quick shout out to Anita. Thank you for putting in a great comment in the chat. Bioinformatics in quantum. I love that idea. Not just me. We are seeing a lot of active research in this field as well. So very recently, a group in collaboration with, I think it was Google or someone, they did a lot of research on doing supercompute for protein folding analytics and how we can use quantum computing to accelerate that kind of process. Along with that, we also have a few startups that are currently working on drug discovery and drug design using quantum computing. The bioinformatics in general is a very interesting field where we see a lot of applications of quantum computing. And the reason for that is very simple, right? The chemistry beneath the bioinformatics has a lot of processes. It has a lot of reactions in general, which are quantum mechanical in nature, which has a direct relation to what we are doing in quantum computing. So because there's a very transparent relation over there, everyone is excited about this field. So spot on. That's a very relevant field that we all are working already on. So I would definitely encourage you to start thinking about this, where your research can fit in quantum computing. And if there's anything that we can do together, I'm always open for collaborations, right? So yeah, let's definitely continue this discussion forward. Okay, yeah. So coming back to what I was saying, right? AI for quantum, that's definitely useful. And one quick example that we want to share over here is, yeah. So one quick example where we want to share over here is the research that we are doing at Advisor. So Advisor, we are a young organization. We are not a legacy old institute. We are still very young, and we like to keep innovating. Quantum is just one of the technologies that we are working on. Along with that, we also have a lot of other things that are growing up and growing at our institute. So if you're ever interested, you can always go to our site. You can scan the QR code over here, thevisor.org. It's a nonprofit based out of DC in the US. And the overall goal is to work on cutting edge science, right? And we all love to do that. We are just providing a platform where we can all do it together. Quantum is just one of the many domains that we're interested in. We do AI as well. It's at a much smaller scale compared to the kind of research that we are doing at Quantum, but still, it's some of our researchers are involved in that. And over the past few years, we have tried to contribute in our way back to the societies. We have provided scholarships to students. We have supported research. We have been tied up with various institutes and universities all across the globe to make sure science is accessible in the most elegant way as possible. We today have students coming in for us from more than 102 countries, which is really commendable, given that the team over here is still very lean and small. We have had fellows working with us. We offer internships, fellowships. We also support professors in their research. We work very closely with the industry. So till date, over the past just 2 years, we have completed 17 industry pilots. And this includes some of the best partners that we have had the chance to work with. We also support startups. If some of you guys are having some startups at a university, or maybe you are planning of spinning off one on your own, we aren't. I'll be honest. We aren't that well established in India to actually fund these startups right from day one. But we are trying to make that happen, right? So that's kind of innovation for the long term. Today, we are already working with and incubating startups here in the US. So there are 3 successful startups. One of them is actually out of India. So that startup was first started off in Bangalore, in India, and then they came to the US, and now they recently started working with some of the best national labs over here. So we want to together find ways to work together. We want to make sure that together we are communicating science and making sure that the best research happens from these legacy institutes, and we're all here to make that happen, right? So that's kind of the vision that we're coming in from. And I keep saying that, but I'll repeat it again. We are very, very grateful to APSHE and the entire state of Andhra Pradesh for giving us this platform to realize that kind of vision in India as well, right? So coming back to my topic, AI for quantum is very useful. And some of the key areas where our organization Advisor has already started looking into is one, for example, how can we use AI for accelerating device design, right? So quantum hardware in itself. Because if you look at a broader picture, the fundamental challenge is that the hardware improvements, especially in the quantum side, requires very, very precise, very, very costly, and very, very extremely difficult experimentation. It's all iterative work. You don't have a lot of simulation tools available today to help out with these kind of device manufacturing. And that's kind of a problem that we feel that AI can be solving in the long run, right? So these quantum systems are very hard to, they are very complex to simulate, they are hard to characterize. And we feel that with some kind of ML solutions, right, we can identify the governing physics behind these kind of devices and combine them with some kind of physical equations to, and maybe use deep learning to learn these kind of equations to guide optimization around that. Maybe we can use AI for, let's say, designing multi-qubit gates, right? Okay, so gates are kind of operations that are used in quantum computing. You don't need to know about all of that today, but just as a idea, right? So we can use AI for automating the design of these kind of 2-qubit gates, multi-qubit gates, so that when they are topped on superconducting circuits, which are the fundamental technology used for quantum computing, it optimizes the entire process, right? It optimizes protocols on how we are handling these kind of control pulses, how we are manufacturing the variability involved in these very complex architectures. So we definitely see a lot of value over here. One area which I would definitely like all of you to explore, if you are working in a similar or tangent field, is AI for semiconductors, right? So how we are using AI for semiconductors and for manufacturing and those kind of things, we can translate a lot of that knowledge directly to the manufacturer and device design for quantum hardware as well. And we want that. We still need a lot of value coming in from the quantum hardware side. There's still a lot of bottlenecks to resolve. So we feel that if we have good ideas coming in from the AI community, this could be really beneficial to all of us. The second problem that we are currently working on is that how can we create more efficient quantum algorithms, and AI could be useful over there, right? And it's a very trivial problem to understand. So I hope everyone can maybe get sense of it. The problem is, you see, these kind of quantum algorithms today that require compact circuits. So the idea is that smaller the circuit of these quantum algorithm is, the easier it can run. As simple as that, right? And the problem is exactly that. Once we start translating your problem into quantum circuit, it's huge. It's very long, and that circuit cannot fit on today's machine, right? And to make it fit on today's machine, we need to compress that circuit. We need to optimize the circuit. We need to make it very compact. We need to reduce the circuit layers. We need to reduce the operations that are required in the circuit, and so on. So how do we do that? One idea which was recently suggested, and it's already been demonstrated in one of the industry use cases as well, was to use some kind of a transformer model between that, right? So the idea is very simple. We use some kind of a GPT model which trains on sequences that are predefined. So we tell the model that, okay, these are the constraints, these are the limitations, and these is the resource pool for all of the operations that you want to do, right? And based on all of those constraints, maybe the transformer model can come up with sequences that are coming in from that predefined pool. So I've already given that entire knowledge breadth to them, and come up with certain operators that are low energy inherently. So what that helps us is we just can come up with circuits that are much more compact. They are much more optimized, and this particular field of research already is being implemented in the industry at a very large scale. So I think there are a couple of companies that are already doing some really interesting work. If I can think of it correctly, we have Qubit, we have Classic, we have IBM, we have a few others that are already implementing AI at a very aggressive pace, uh, in where they can help quantum algorithms, right? So very interesting area. This would be really important for anyone who's already using AI for computational experiments, right? So someone who's more familiar with computer science, with mathematical backgrounds on algorithmic structures itself. I think you guys can be really helpful for us in understanding where quantum computing can be used for circuit designs, for optimizing the quantum algorithms, and what. Yeah. Yeah, so moving on. Another use case which we see a lot of interest today is in automating the device control. And I love this use case because 7 months back, and this is a true story, right? 7 months back, I was speaking at a conference, right? And I had a similar slide talking about automated device control and where can AI be helpful over there, right? And one of the audience members came up to me after the conference, and he mentioned that, hey, this is a very interesting idea. We're already working on device control. We don't do AI, right? We are a startup that's focusing purely on quantum hardware device control and control electronics and optics and a few other things, right? So he came up to me with a proposal that we know everything that there is to know about quantum hardware. Tell us where exactly can AI fit in, and we'll try to make that work. And we had a good chat. we had a good chat. I could not help him directly, unfortunately, but he was so motivated. And I recently had a call with him, and he has now his own startup that's working at. They recently raised, I think, a few $1 million. They're based out of somewhere in the Europe, I think Finland or somewhere. But they recently raised a ton of money, and they are doing exactly this. Exactly this, right? So this is no longer an idea. This is actually something which startups are building on. So the idea is very simple, or I should say the technology is very straightforward. And it says that for automating a lot of these hardware processes or control processes that are between the quantum hardware and to your actual measurement stage, a lot of fine tuning is there. And this is traditionally a very manual process. So a lab technician actually sits down over there and they have all these control knobs where they have to fine tune everything manually. The alternative to that is just have some sort of an automation engine in between these two layers, right? So the hardware sits on the left-hand side, the measurements and the entire software stack is on the right-hand side, and in between there's some kind of automation tool that first understands what the constraints of the hardware is, and this could be a real-time thing as well, right? So that's something that hasn't been done. Maybe you guys can do it tomorrow. So the real-time analysis is still very difficult to understand what kind of state the qubits are in today. What's exactly the noise environment that we're working on at that real time instant? What are the different noise and the different environmental factors that is affecting the quantum machine today? Because quantum hardware in its very inherent state is very susceptible to everything that's happening around it. Right? It's not like a classical computer which can work everywhere and anywhere. These are very specifically designed complex machines that are isolated from the environment. So if there's, let's say, very high temperatures, it could affect the qubits. It could affect the quantum computers. Maybe there was an earthquake nearby, right? And just the vibrations were so big that it affected the kind of qubit states that the quantum computer was in. So environmental factors are definitely very, I would say, susceptible to noise factors in quantum computing. And if we have some kind of an automation system that helps us understand these kind of factors in real time and accordingly optimize the control electronics that are governing that, I feel that it could be a huge, huge game changer. So this is definitely another area where we see a lot of interest coming in from the AI community, at the same time from the quantum community as well. And together we need to just find out a way to make this work, right? So definitely a very interesting area to all of us to work together in. Another, maybe this is one last area I would like to mention about is that using AI for quantum error correction. And if you're not familiar with quantum computing, this might be a little bit non-trivial to understand, and the reason for that is classical computing today is at such a great level of error correction that we no longer pay any significance to it. So the thing is that even today, classical computers, when we work on bits, there is a chance that some bits in your computer might not work perfectly, and that's okay. But the error correction routines are so well designed today that even if a bit is incorrect, or maybe it has a fault, or it has some kind of error, it can be corrected real time, and it does not affect any kind of processing that actually gets done with those bits, right? That's unfortunately not possible today with quantum computers. So if some qubit is behaving incorrectly, it spoils your entire calculation. It spoils your entire measurement, entire analysis, entire results that are coming out of it. So every single qubit is very important for us. So one way where we are doing tremendous amount of research, and a lot of research is actually happening in India as well at very different research institutes, is that the quantum error correction routines are definitely a very useful tool for today's NISQ era computing, right? And the way we can maybe see them improving further, and when I say improving, I basically mean that their efficiency is better, their turnaround times are better, they are faster, more accurate, much more resource intensive. So we see that some kind of AI tools can help understand these noise levels and noise extraction levels from the quantum hardware and help us design much better quantum error correction routines as well, right? So as I mentioned, right, so I am not at all an expert in AI. I'll be very honest to say that. So it is all of your uh, domain, right? So you are the people who are going to tell me that, yeah, this is an area where AI can definitely help. And when I say AI is a very, very generic, huge term. So what exactly do you mean by AI, right? Is it machine learning? Is it deep learning? Is it reinforcement learning? Is it something else? It's a very simple classification task that I'm working on. So you are the ones who are going to tell me that, and then I can share you the use cases. Okay, this is where we are struggling with quantum. This is where we very trivially understand that maybe quantum is helpful, but at the end of the day, it is people like you who are going to help us with this kind of research. That yeah, AI is definitely useful over here, and let's work together to make that a possibility. Let's find ways to create applications which are not only useful for the quantum industry, but also help in accelerating the entire quantum ecosystem. And whether that has to do with small applications today and eventually transforming the entire quantum industry tomorrow, or whether it is standalone applications that can actually spin out your own startup, whether you want to work with different companies on these kind of problems, it's completely up to you, right? So we today's session over here, it's not one way. It's not supposed to be a place where I am trying to uh, pull a lot of knowledge and throw it to you. It's rather a conversation where I want to encourage all of you to start thinking about this, right? Start thinking about the various areas where quantum can be useful, and AI can be then useful for quantum computing, right? So with that, I think I'm at a stage where I'll start wrapping up these ideas. And again, this would be maybe a good time to start putting all of your questions down in the chat so I can start picking them one by one. But just wrapping up my session over here, the last section of today's talk would be on some really crazy ass ideas that we are working on over here, right? So as I mentioned, quantum is the future. And not only globally, but also in India, we are seeing a huge, huge demand, not only from an industry perspective, but also from equally from an academic perspective. And one reason for that is the national government pushing it like nothing. Honestly, I haven't seen this kind of pace at which, especially India, works in a very, very long time. And I'm really happy. I'm really glad that this is happening in the country. We have had a massive pool of 6,000 crores rupees allocated only for quantum for the next for this particular decade, right? For the next 5 years or so. And the mission is that we want to make sure that quantum computing, quantum sensing, quantum cryptography, everything around this quantum tech stack is developed in India, for India, and for the entire world. So I love the mission. I really see a lot of talent coming in from India for India. We have already have a lot of thematic groups and technical groups being established all over the country. And if you try to zoom in a little bit more, right, you'll understand that AP is already leading in this race, right? So we already have a lot of uh, tie-ups and a lot of institutes being popping up in that region of AP. Along with that, we have tremendous support from the government of Andhra Pradesh itself. So this was the flagship MOU that we recently tied up with the government of Andhra Pradesh. APSHE has been a tremendous role to play in this entire organization. So we are setting up our first quantum education program in just in just 2 days. Okay. Today is December 6th, December 8th. This particular course launches, so this is open to all. And this would be a very fantastic initiative to at least get started with quantum, right? So there are no prerequisites involved. We do not expect everyone to come into the program and become quantum experts at the end of it. This would be a very high level course. But the idea is very simple, right? You come in, you get a feel of what it is about quantum computing, right? It's like when you hand a cricket bat to a kid of 2 years old, right? They won't become the next Sachin Tendulkar, but they would at least get a very close feel of, okay, I have this bat, let me just try playing with it. So that's going to be our very vision over here as well. We'll just throw you into the deep end with the sharks, and we'll throw a lot of quantum applications from some of the best people in the world. not just academicians, with all the founders, the CEOs, CTOs from some of the best quantum companies. We'll have an amazing, amazing cohort lined up for all of you. It's not going to be an easy journey. It's going to be really tough. And it's open to the faculty as well, right? So I just got a comment in the chat. It's open to students, it's open to faculty, it's open to anyone and everyone. So please, I forgot to put in the link over here, so I can share the link afterwards, so you could just do a quick Google about Wiser and Quebec and Apche and the Amravati Quantum Valley, and definitely enroll for that. It's going to be a fun learning experience. And even if you're not enrolling, I know you all are professors, so you have really, really busy schedules. I respect that. I truly understand that. Maybe watch a YouTube video here and there, right? Just get aware with what quantum technology is all about, because this is going to be the future in the next few years. And it would be really, really amazing if you can bring your own domain knowledge, your own industry expertise to this field. Because if you're all working together, there are some really amazing problems for all of us to solve together. So the future is going to be a combination of quantum for AI. So the scenario today is that we need AI. We need all of you people to help us with developing quantum. But once quantum is good enough, once we are at a stage where quantum is noise tolerant, it's really big, it's helpful for solving all the problems, it will give back to the AI community, right? So don't feel like I'm being very selfish over here and asking for all of your help. Believe me, once the quantum is matured enough, we'll give back to you. We will contribute to success for AI as well, and much, much more. Right. So again, I keep coming back to the same topic, that the future is not going to be purely quantum. It's not going to be purely AI. It's going to be a mix of everything that's available to us today. So there would be problems that are better solved on AI. There would be problems that are better solved on classical HPCs. And there would be a certain set of problems that are better solved in quantum computer. But to just get to that stage, we definitely need an intersection between these kind of technologies happening today itself. Because if we are just delaying this, we would take much, much more longer to get to that stage. And the interesting thing over here is that once we have that kind of scalability, once we have that kind of maturity in the quantum technologies, the kind of problems that we end up doing is just huge. For example, this is the kind of problem that we are currently working on at Wiser. So the amazing machine that you see over here is a nuclear submarine, and the scale of it is just huge, right? So the tiny dots you actually see on the top of the submarine are actual people, right? So maybe with that you can imagine the size of this entire nuclear submarine is. So nuclear submarine is today, I feel, one of the most complex machines and one of the massive machines that humans have ever produced. Nuclear submarines work on a very fundamental, on a very fundamental concept that they don't need anything else to power them. The entire propulsion systems are powered by nuclear energy. So these are miniaturized, smaller nuclear reactor systems that help propel this submarine. And the best thing which I have heard in a very, very long time about these nuclear submarines is that they have infinite time duration of staying underwater. Let that sink in, right? I'm not talking that they can stay underwater for 2 years. I'm not saying that they can stay underwater for 20 years. I'm not even saying that they are underwater for 200 years, not even 2,000 years, not even 20,000 years. They are literally have the capability of being underwater for infinite amount of time. They never have to come to surface for refueling, because nuclear reactors are built that way, right? That's kind of technology that humans have been able to produce. And now I was dumb enough to ask this question to one of the chiefs when I was working with this team, right? And I asked them, okay, so that's interesting. So do they always stay underwater? Right? And the chief in front of me started asking and laughing about that to my comment, and he very humbly replied that no, these submarines actually do come out of the water. And the reason they come out of water is only twofold. The first reason is that uh, the resources need to be replenished. So the food supplies, the clothes, the machinery, they need to be oiled again. They need to be the surface defects need to be corrected again. So these kind of small problems need to be rectified. So that is one of the major reasons that this submarine actually has to come out of the water. And the second reason it comes out of the water is that uh, the people working on the submarine need time to reconnect with their families, right? They also need to break. They also need to go back to their homes with their loved ones, just connect back with the entire human civilization. So that's the second reason why the nuclear submarines ever need to resurface, right? Fun fact: India also has nuclear submarines. We have a fleet of them, and this is like some of the biggest technology challenges we've ever had to overcome, right? So quantum computing is being used over there to understanding how these nuclear propulsion systems are governed. How can quantum technology be so precise, help us in accurate technology calculations at a so good level that these submarines, when they're underwater, they don't need GPS navigation system. In fact, they cannot use GPS. They have to rely on some alternative method. So what alternative methods we have? Can quantum sensing be used over there? Or can quantum computing be helpful for simulating propulsion systems so accurate that we don't need anything else, right? So these are the kind of active challenges that today we are fortunate enough to work on. But that's not all. A nuclear submarine is good, but that's not all. We also are working on EVs. So this is another very interesting area where we have started recently working on. So EVs, I am sure that's not new to India, right? Since I've landed in India, everywhere I see there are a lot of now electric vehicles roaming around the roads. Especially in AP, I was in Vizag for some time. I was in, I think it was Vijayawada for some time. And in both the cities, I just loved seeing how quickly the population has adapted to electric vehicles, and that's amazing, right? But to make sure that these electric vehicles are sustainable in the long run, we need better batteries for them, and that's a huge bottleneck today. Every battery company is working very extensively on that. And not just battery companies, every electric vehicle company is working extensively on that because that's a huge bottleneck today, right? If the batteries are not good enough, they degrade very quickly, they lose their charging capacities over time, and quantum computing could be useful over there. So we need to find ways where quantum computing can help simulate these batteries at a much more faster pace, at a much more accurate level, so they can ultimately be helpful for these kind of EVs and for these kind of applications. Another very interesting area, and I just put down a collage of the different kind of other activities we are doing, is quantum for warehouse optimization. So in India, another thing I loved, and this is something I would definitely miss once I go back from India, is that uh, the hyper local deliveries that have started recently, right? So Swiggy's and Blinkits and Zomatos, love them. I have kind of gotten addicted to them. But the way they are possible is because of the huge warehouses that they maintain. And in the US or somewhere in the Europe as well, we have huge warehouses. The one you can see on the top left-hand side corner. So these are kind of warehouses which are automated as well, right? So these are so huge that if you maybe combine 4 or 5 massive scale football fields together, they would create one warehouse. That's kind of scale these warehouses operate. And it's very difficult for them to have manual labor actually do all these manual processes on these warehouses. So they have automated these warehouses. So they have tiny robots collecting and storing and picking things from there. So as soon as you order, maybe on an Amazon or maybe on a Alibaba or somewhere, your order gets registered to these warehouses. They are small robots which find your product, pick it up from the stack, put it in a parcel, and then ship it off to the delivery courier service. And then they take it to your doorstep and to a courier, right? You should actually watch some YouTube videos about that. It's very fascinating how these warehouses are operating. But a huge challenge in these warehouses is that controlling robots. Controlling robots in an efficient manner, in an efficient logistical way, and quantum computing is being helpful over there. So we have certain quantum algorithms that are currently being run by these warehouse optimizers to make sure that the routes these robots are actually running is as optimized as possible. So on a very trivial level, just try to understand it as a car moving around in a city traffic, right? It needs to find the easiest way out of there in the quickest time without bumping into other cars or without taking much more fuel. So the same concept applies over here as well, right? So robots need to pick up the right product in the fastest way possible, because now we have 10 minutes delivery. So the robots need to be really, really quick. And at the same time, they need to avoid bumping into each other, avoid damages, avoid extra energy consumption, so all of that as well. So quantum computing does a pretty good job at optimizing stuff, right? So we just put in the constraints, we put in the mathematical formulation, the Hamiltonian surrounding these kind of problems, and then we let the quantum algorithms do their job. The image on the right-hand side over here is a quantum sensor. So quantum sensors, at least the magnetometers, are still huge. So our job is to try and miniaturize them. So there's a lot of effort being done into miniaturizing quantum sensor. That's more of a hardware thing, but I still wanted to give a quick glimpse of the kind of technologies that we're working on. Similarly, quantum communication, that's on the bottom left-hand side corner. So how do we quantum secure satellite communication? Because there's a huge threat looming around the corner that if quantum computers are so powerful, they just might crack our today's encryption. And if that happens, we would have to go back to old days and actually communicate via letters and postcards. And we don't want to do that. So digital communication still needs to be encrypted in a very, very strong manner. And that needs a little bit help from quantum as well. So we have something called as a QKD, quantum key distribution, which helps in encrypting digital technologies, digital communication. And one way we see that happening is just communicating it at the very highest level, at the satellite, right? So if that is encrypted, automatically all the levels below that, all the layers below that, are safe in some sense, right? So we are definitely working on that as well. So these are some of the kind of examples and the kind of technologies that we are today working on at Visor. And I would, again, humbly request everyone to start thinking about these ideas, start thinking big, start thinking crazy, start working on these kind of huge projects, because the future is going to be an intersection between AI and quantum. And don't get me wrong, this is not at all a boring process. We are not all nerds. So we have a lot of fun. We try to work at some of the best labs in the country. We try to be there at most conferences, and overall just have a fun time being together. Fun, loving people. Right. So that would also be a call for everyone who's here and who might be interested in working with us. Do reach out to me. We are very open to collaborations and starting new projects. We are always open to that. So as long as there is somewhere where we can work on or collaborate and give back to the society, give back to the scientific community, we are open to that, right? So with that, I'll wrap up today's presentation. Hope that the last 60 minutes or so was useful. You took something or the else. I don't expect everyone to be a quantum expert by the end of this 60 minutes, but at least I feel that you all would take away something or the else, right? Or at the very minimum, get at least the idea that quantum computers are around the corner and everyone should start working on that. Right, so feel free to take a screen grab of the slide. My email address is over here. You can always reach out to me. My QR code is also present on the screen, so you can easily take a snapshot and connect with me on LinkedIn or some other platform. Always open to chatting with amazing people like you. And with that, I'll thank you for inviting me over here. This has been a great pleasure. Thank you, everyone. Once again, thank you, Akshay. Thank you, Anilji. Thank you, Madhuji, for inviting me over here. You guys are doing an amazing, amazing job. Very humble and very proud of making this collaboration possible. And at the same time, thank you. Thank you for the tremendous support that you have expended to us. We understand how difficult it is for an external organization like us coming in from the US to start setting up processes in India. And yeah, you guys are awesome, right? It could not have been without the continuous support of Apshit. So we are tremendously indebted to all the efforts that you're putting in behind the scenes. We have also had a small startup here in India working with us and helping us with all the ground processes. So I'd like to give them a shout out as well. Cubitech, it's a young startup, but they're already doing amazing, amazing work. So if you're ever interested in working in India in quantum, you should definitely look this startup up. They're based in Hyderabad, very, very close to AP. Right, so we should look them up as well, Cubitech, and those guys are doing some amazing work as well. So together, we want to make sure that AP stands for quantum, AP is the hub for quantum. AP is the center for quantum. Amravati is the center for quantum, not only for AP, for the entire country of India, but also for the entire world. So with that vision, I'll wrap up my discussion here today. Thank you, everyone. And if there are any questions, I can stay on a few more minutes for that. Thank you.
Hello.
Yes. Yeah.
Vardhanji. Thank you very much for sparing your time. Dear participants, I would like to tell you one thing. Actually, maybe he is working day and night. He is working for India during the daytime and for US during the night time. So there is definitely we have to take you as a role model uh, in terms of work culture. Thank you very much. And we look forward, sir. Just I want to tell you today, in the presence of three VCs, vice chancellors, and the principals, NRF coordinators, around 200 colleges participated there. We have also released the brochure for this Wiser Quantum program. Definitely, I would like to mention that AP will be number one question in the days to come.
Sir, you are not audible, Anil.
Yeah, thank you. Thank you, everyone. Thank you for being here. If there are any questions, please feel free to put them in the chat, or if you want to unmute yourself, that's okay as well. I can happy to stay on for a few more minutes to answer any questions that you might have.
Sir, good morning. Hello.
Yes, please.
Hello. Sir, am I audible, sir?
Yes. Yeah.
Sir, yeah, really, it's a very amazing and nice presentation, and we are bubbling over to be a part of this. But the thing is, when we get this quantum computing into the real world and the real applications, is there any what? At what time?
Yeah, please go ahead.
At what time it's going to be in physical? In physical, we'll get into the applications of quantum computing and all.
I love that question, and honestly, I don't have the best answer for that. I'll give you 2 points. Maybe that would make it clearer for everyone over here. So the first point is that quantum computers are already a reality. Right? It's not just a dream anymore. In fact, India will have their first quantum computer coming in from IBM in 2026. It's already been finalized. It's in the process, so you can think of it as a ship bringing it from the US. It's just taking its time, right? So the first quantum computer will already be in India, and in fact in AP, in Amravati. So that's a huge news for everyone over here. So the first quantum computer will be coming to India very soon. Quantum computers till date have already been there. So we have about 20, 30 odd quantum computers in the entire world, some in the US, some in Europe, in Japan, in Korea, maybe Singapore as well. So there are different places where these quantum computers are located. So that is one. The second point I would say over here is that we don't need quantum computers on a personalized level, right? So we won't ever get to a stage where they are replacing your laptops or your mobile phones or something like that. They would still be centralized locations. So try to compare them with how supercomputers are working today, right? Like India has a lot of supercomputers and they are state of the art. They are amazing, but not everyone has it at their home, right? Not every university has it in their campus. Some universities have that, and that's good enough. But most of the people would be accessing these supercomputers through cloud access, right? So very similarly, quantum computers will also function. They will be located at central locations where they're monitored, governed, and made sure that they were running at all times. And then there would be cloud access available for everyone to use them. So that would be point number 2. Point number 3 would be if quantum computers are ready today, are we already working on the applications, or when can we expect applications to be to be implemented on them. So the answer over here is yes and no. So we are already working on applications. So the applications I just showed you in the past few slides, we are already working on them. Are we getting a quantum advantage already? No. So we are still a few years away from getting a real advantage where we can actually say that quantum computers is better than classical computers. What is happening today is that we are maybe getting comparable results, right? So quantum computers can solve at least at the same pace or maybe slightly slower than classical computers in certain use cases, right? And that's I feel is a very promising thing. Because if both the things are on the same level and the classical computers cannot go any faster, there's a lot of scope for quantum computers to go faster, right? So that's the kind of scope that we are all betting on. So I would say that applications are already being developed. Definitely look into that. Research is happening at a pace faster than anything that I've seen before. So we have a lot of a lot of demand on fundamental research, on application research, on algorithmic hardware research on quantum computers. And we need better quantum computers, right? So even though we have quantum hardware today, we need better, bigger systems available very soon. So yeah, maybe that helps answer your question.
Really, it's a classic, fantastic answer for the question. Thank you. Just I want to pose one more question. So, as a part of quantum mission, what is the role of academicians? Being a part, we are working as a faculty. It's a domain for these various colleges. So, how will be a part of this quantum mission, and how we'll get the results of fruits of the quantum mechanics and quantum computing into our own lives?
Role of accommodations, I honestly feel that without you guys, the country won't run. Okay. Quantum is still a very early field, right? We still need a lot of fundamental research going into that. And the industries do not have that capex, or they don't have that bandwidth to support that kind of fundamental research, right? The ultimate responsibility falls back on academia. We are seeing, the good news is that we are seeing more and more funding coming in through industry participants, because industry sees a really good ROI at the end of that. So they feel that if they invest today, they can have their own quantum computers, and maybe in a few years' time, they are the industry leaders and they have their own compute processes to run some of the biggest problems. But still, majority of the research is happening in academic environment. So the government is really supportive of that, at least from what I've heard. And please don't quote me, because I'm not the best expert for how the National Quantum Mission is being governed in India. But from what little knowledge I have, they have been supporting academic institutes very, very thoroughly. So there are grants available, there are opportunities for spin-out startups coming in from academic institutes, there are collaboration opportunities, there are specific funding available for setting up quantum projects, right? We also have some funding available for setting up quantum labs. So if you are at a university and you feel that there is a need to set up new quantum labs at your university, at your institute, there are government grants available for that too, right? So there are a lot of things available. And maybe one quick thing which you should definitely look up is the National Quantum Mission website. I think it's NQM at the DST or something like that. But yeah, definitely look that up. There are a lot of active opportunities available today. Along with that, especially since this cohort is primarily based off institutes in AP, there are a lot of new things happening in Andhra Pradesh as well. Recently, there was a quantum policy announced, and that policy gives a lot of benefits to new startups that are coming up. It gives a lot of benefits to academic researchers who are working in this region. So try exploring a little bit around. I'll say I'm not the best person to answer this, because I also have very limited knowledge. But try to find people. I'm sure the VCs from the institutes who are joining in, or at least VCs who we can reach out to after this call as well, they would have much more knowledge on how this entire national quantum mission is being governed, or at least they would have the right resource person available to them to guide them through this process. But yeah, the bottom line is there are a lot of opportunities. You can definitely make the best use out of that. How do you get started? I would say to start identifying where you want to work in, right? What is your core area of specialization? Whether you want to work on the software side, on the hardware side. Try to create bridge between your current research and the quantum research, right? What is the tech transfer that's happening over there? what kind of knowledge can be easily be communicated from your classical counterparts to the quantum counterparts, right? So once you have all these answers, you can immediately start applying for these kind of funding opportunities from the government themselves. And once you have that, you can start setting up your own quantum centers at universities. You can start having quantum courses deployed for students. You can have your own research that's specializing in quantum. You can have quantum labs. You can have center of excellences for quantum technologies, right? So the possibilities are limitless over here. The ultimate goal is to have technologies that is good enough, research that is good enough that can help. So the goal over here is not to publish papers. I know all of you are very fond of doing that. I've been I've gone through that academic process, and I've been a culprit myself of publishing many papers which just get lost in that academic sea. But today the goal is a little bit different. We need more IP coming out, right? We know we need more information that's actually being applied to the industry. So we need a lot of help from academia, but just in a different way. And I am very hopeful that all of you over here would be the champions and the leaders taking this forward. Yeah. Any more questions before we log off over here?
Yes, sir. I think there were no more questions because we all will connect with your this thing. If any queries are there, definitely we will share their queries to you also. And thank you very much for joining us and enlightening us on this quantum education in the area.
Sure. Yeah. Thank you. Thank you. Likewise.
Thank you, sir. Let's close this. Thank you very much.
Sure.